Let's get a little bit more quantitative about the relationship between delta G and K. I showed you the fact that delta G and K have very different kinds of amounts, of magnitudes. Delta G's are tens, hundreds, occasionally thousands of kilojoules per mole. K values, on the other hand, can be very, very large exponents, 10 to the minus 47, 10 to the plus 83. So what is the mathematical relationship that allows us to connect these two? There has to be one, because whether I'm talking about free energy changes that drive a reaction or concentration changes that drive a reaction, in both cases I'm doing thermodynamics. So it's just a matter of finding out what that relationship is between the kilojoules and the molarity. And so let me go ahead and write it down for you. Actually, this is not all that intimidating an equation for us to work with. Notice, first of all, that it has our friend RT here, and we know what these values are. Typically, R is 8.3 joules per mole Kelvin, and temperature is in units of Kelvin. It'll be at room temperature, say 300 Kelvin. So we know what this particular value is here. It's about 2,500 joules. So that's a big multiplier for one thing. That means that we need to take into account that factor of 2,500 as we compare delta G to K. The other factor we have to take into account is that we have this log of K function which tends to compress our result. In log base 10, for example, if I have something which is 10 to the 20th, then that's a value, if I take log of 10 to the 20th, of 20. So I can actually take a very large number and knock it down by having a log function associated with it. And that's what we typically do. By having that natural log function there, it takes a very large exponent and it knocks it down and making it into a number that's more manageable in terms of joules. Now, the other thing that's important to notice is that there's a negative sign sitting here. This negative sign sitting here is what allows us to convert delta G negative for spontaneity into a positive value when I'm looking at the exponent associated with the equilibrium constant. So we can go ahead and do a little bit of math here on these, and I'll show you some examples. So here we go. The free energy of a particular reaction is minus 170 or so kilojoules per mole. I want to know what K is. Now, before we start this, we have to predict what we think this is going to be. First of all, I know that because delta G is negative, this means this reaction is spontaneous. It means it's going to shift to the right. If it means it's going to shift to the right, it means that the stuff on the right-hand side is going to be bigger than the stuff on the left-hand side, so I'm going to end up having a number which is greater than 1, which means that my exponent is going to be a positive exponent. I also know that because that's a pretty healthy chemical reaction in terms of free energy change, that I should expect to be seeing a pretty large exponent for my result. So I'm going to go ahead and stick the numbers in here, and when I do that, I have minus 8.3 joules that's associated with my R value, 300 Kelvin or so for the room temperature, log K. So I've got to do this math problem right here to get my answer. Now, if I want, I can go ahead and step my way through here mathematically as I rearrange all of this to extract out the K value. So here I have delta G is minus RT log K. I pull the minus RT over to the left-hand side, and then I multiply everything through by exponents. After I've multiplied everything through by exponents, I end up freeing up my K value, and it's equal to e to the minus delta G over RT. And then I have to make sure my kilojoules and joules match up. And so that's what's taking place inside this mathematical expression here. I have my minus 170 kilojoules times 1,000 to get it into joules, divided by RT. And there's my result, 3.5 times 10 to the 29th. The thing that we need to stop and appreciate is that we predicted this value before we started. We knew it was going to be a large positive exponent, and sure enough it is. It's always good to be able to do this, because if you can do that estimation first, it helps you to avoid stupid mistakes like forgetting your negative sign. So that minus 170 kilojoules per mole, very spontaneous process produces a very high ratio of stuff on the right to the stuff on the left in the calculation. You may have seen in the last example I showed you the fact that I did some simple mathematical tricks to be able to clean up and rearrange an algebraic expression. The trick I used is the use of inverse functions. And it's important to use these inverse functions because most of the calculations we're going to be doing here in the spring semester involve the use of exponents, exponents involving 10 to the x, e to the x, or the log base 10 sorts of functions. So if I can just show you this here, this is something you learned in high school about inverse functions. If you take two inverse functions and you multiply them together, you are able to basically remove those functions and leave whatever it was that was sitting inside the function to begin with. So if I have a function that's e to the x, in this particular case, I multiply it times the natural log function. Natural log and e to the x are inverse functions, and as a result, x gets pulled out. Similarly, if I have a log function, then I take e to that, and I can pull x out as well. This is what I did. This particular expression right here is what I did to pull out my k just a moment ago so I could find delta g. You're probably more comfortable seeing it in log base 10. So here I have 10 to the x. I take log base 10 of 10 to the x, I get x out. So as a simple example, if I've got 10 to the minus 5, log base 10 of 10 to the minus 5 is minus 5. Or if I have the number 5, log of 5 here, then this becomes 10 to the log of 5, and I end up with 10 to the 5th.